Okay, you probably already know that anytime you have a linear factor, this is how you factor it. However, if you have an irreducible quadratic factor like this one, then you need a linear nominator. Okay, if you have quadratic, you need linear. However, if you had cubic here, then you would start with quadratic, right? What does that tell you? That you need to reduce the power of polynomial that you have in the denominator by 1 and put that in the nominator. The difference between the powers of polynomials between numerator and denominator has to be 1. Exactly 1. That's what's important. Not that there's linear here or quadratic there. It depends, depending on the power of polynomial in the denominator, okay? That's what matters. There's a really good reason why it needs to be the difference between the powers of polynomial needs to be 1, and it is not covered in a lot of textbooks. In fact, I haven't found it in any calculus textbooks, the actual mathematical reasoning for that. So we're going to prove it in this video. However, I encourage you to choose this as your maybe research project because it's a very juicy topic. You can write a lot about that. I'm going to use linear algebra proof and mainly logic, not very much linear algebra, okay? We're talking about irreducible quadratic. That's the new thing here, okay? Because this was covered in previous videos. So we're going to solve this problem, and yes, it's going to turn into a calculus problem. Right now, it's not. I just want to really illustrate and highlight how much of an algebra problem this is and not a calculus problem. It's going to turn into a calculus problem on the second page, but here we're just going to see if we're good enough to solve an algebra problem. And if we are, then the calculus part is pretty simple. Okay, so here I'm going to copy paste that and then just worry about this side, okay? So the common denominator is the product. Naturally, because this is the common denominator, I have to maintain that left side of the equation equals the right side of the equation, okay? If this step is a little challenging for you and you need a little refresher, I have a little memory refresher there, okay? This is the step that I kind of skipped, so we meet here. If you want to screenshot that, you can. The idea is that you find common denominator and then you compare this fraction to the common denominator and choose the least common factor. This fraction has x minus 2 as a factor. It doesn't have x squared plus 1 as a factor. So you give her that, okay? And this fraction has x squared minus 1 as a factor, but it's lacking x minus 2. So you multiply that by x minus 2, okay? So that's the step that we skipped. So we meet here. With the partial fraction integration, you're never worried about the denominator. You can cancel it, you can ignore it, think of it however you want, but let's just focus on the top part. And you see, I demand that the left side of the denominator equals the right side. Okay, that's what I'm working on. Now, let's open parentheses, plus p plus qx times x squared minus 2qx plus rx, like a pill. Okay, so that's the equation. Now I have 3 unknowns. I need 3 relationships, and I have different sorts of things going on. I have x squares, I have linear x's, and I have just constants, okay? I'm going to underline x squared terms and use this idea that linear x is not going to contribute to x squared terms. So I can set x squared terms on the left side equal to the right side. And then I'm going to pick out linear x's. That's it. And then I also have constants, but on the left side, there is no constant, so that must be 0, okay? So this way, I can write down 3 equations. Okay, so usually whenever you have irreducible quadratic factor, like we did here, you end up most of the time having to solve a system of linear equations, and you're probably asking what's going on with the squares. And I'm going to set x equal to 1 for the first and the second equations, because x takes on any value from the real number set. So I'm going to let it be the value that makes my solution simple. And definition of simple is linear, in my humble opinion. Okay, that's one relationship. That's second relationship. And this one is going to give me a really useful relationship. It gave me this idea that P equals 2 times R. Okay, so then I'm going to replace this P here with 2R, because it told me that it is synonymous to say 2R or P. Now I'm going to isolate Q. Okay, I'm going to say that Q equals to 3 minus 2R. And I'm just going to say like that. Okay, then I'm going to pop this Q equals to 3 minus 2R right here. It looks like I can find R first, because in this equation, there's only one unknown, which is R. So I can maybe work on that only. Okay, so for equals, I'm going to open the parentheses. So that is -6, positive 4R, positive R. Okay, 6 comes on the left side. That is 10, and this is 5R. Well, looks like R equals 2. Okay, then I'm going to find Q, 2 times 2, which is R, we just found that, and that is -1. R is 2, Q is -1, and P was 2R, or 2 times 2, or 4. Okay, so we found all 3 of the unknowns, and what happens now? Well, the question asked to find the sum, okay? And that's easy enough, even though we don't need to do that, but why not? It takes 1 second. So that's done. Now the calculus part comes in, and you needed those constants to put them here, right? P was, what was P? P was 4, this was -1, and this was +2, okay? And now you can take this integral and that integral. Notice that you cannot take this integral at all, with no rule. This integral, however, is one of the basic rules of integration. It's just ln x minus 2. That's all it is, and P comes out of the integrand, because that's the number. And this one, we'll see what that one equals to. But simple, basic rules of integration type of integrals, well, this is hard to even look at, okay? So this whole thing, notice that just getting the coefficients, which is the partial fraction decomposition part, is an algebra task. This is where the calculus starts, and I have already solved it, but I'm going to take you through it step by step, okay? So P, we understood that was 4. Q was -1, or just -x, and then R is 2, okay? So what's happening here is that always, anytime you have addition or subtraction within the integrals, if you have terms being added inside of the integrand, you can always take separate integrals of those terms and add them later. This is the feature of integration as an operator. It's linear as an operator because you can linearly add areas, right? So the first integral, u substitution, is optional. 4 obviously came out of the integral because that's constant. So this is basically du over u, because du equals dx. That's why it is optional to do u substitution. In the second integral, don't forget there was minus here, because there was q there, right? And q equals -1. And that minus needs to be maintained in your answer. But here for the second one, u substitution is probably recommendable, because you do get, after you take derivative of your denominator, you do get 2x dx. So du over 2 equals x dx, which is something you have already given to you in the denominator, okay? The only reason you're doing u substitution to this integral and not this integral is because derivative of your denominator is sitting in the numerator there. They gave you u du here. That's why. Here, this one is already matching one of the basic rules of integration. It is arctan, okay? And what happened here is I actually have a video, video on all of the techniques that you use to fit integrand into one of the basic rules of integration. And this trick is very frequently used trick where you are able to separate the numerator so that you get what we kind of did with decomposition. You get a sum of two fractions instead of a single fraction, right? And of course, they're going to share denominator, right? So you get that. These are simple, easy, basic integrals to take, and this is the final answer, okay? We're not done with this problem because even though the SAT problem gave you this idea here, your Calculus 2 problems are not going to give you this side, right? That side is going to be up to you to determine. It's only going to give you up until here, okay? And the most important thing that they gave you here is probably this fraction right there, because that's where most of the people would make a mistake. They might be tempted to write Q there, or for you, these would be these letters, but of course letters don't matter. So here in this video, we're going to prove that this should never be Q, okay? And the proof that I offer you here is a linear algebra proof that uses very little linear algebra and a lot of logic, okay? So we're just going to go with a wrong assumption. We're going to assume that you don't need 1 degree less polynomial in the denominator. You do, but we're going to go with a wrong assumption that you don't need that. We're just going to put a number there, okay? We're just going to put Q there. That's what you do when you have a linear factor. That's what we're going to do when you have a quadratic factor, okay? And see what happens. We're not going to make a mistake in our solution, and then if we end up with a contradiction, we know that we have made a mistake in one of our assumptions, okay? Because that's how mathematics works out. It has perfect logic, so if you don't make a mistake in your solution and you end up with a contradiction and finding that a known fact is being contradicted, you know you made a mistake in one of your assumptions, okay? It always works out beautifully like that. So now, just going to go through with the solution, which we already done, but now with the incorrect assumption and see what happens. Again, forget about the denominators. This step, I'm going to open the parentheses and I'm going to underline like terms. That's all I have in terms of x squares, all I have in terms of x, and these are the constants. And on the left side, I don't have any. Okay, 3x squared on the left, on the right, px squared. 4x equals qx, and 0 equals p minus 2q. All right, allow x to be 1, because that's always nice. Okay, so p equals 3, q equals 4, and p equals 2q. So 3 equals 2 times 4. 3 equals 8. Well, that looks awful, because we know that it doesn't. So one of the assumptions I've made led me to have to contradict a known fact. 3 does not equal to 8. So then must have made a mistake there, okay? So this is a linear algebra proof because this is not linearly independent equation, okay? And when you take linear algebra, if you haven't taken it already, you'll see that this has to span space with enough dimensions. And what is enough dimensions? This divide modulo denominator, or divided by, this synonymous denominator, okay? So the difference between the powers of polynomials in the numerator versus in the denominator has to be 1. If you have 50th power there, you start with x raised to the 49th power, 38th, and you include every term until the linear term, x, and then a constant, okay? Okay, there is the solution. If you want to take a screenshot, there it is, but I will include the whole solution in the PDF in the description box. Thank you so much for watching. Bye.